I'm going to start this by providing us with a reminder of the definition of acceleration. Acceleration is defined to be the change in velocity divided by the change in time. Now, so far, we've been talking about acceleration as being either an increasing or a decreasing speed in some direction. We started off with one-dimensional motion. If something was increasing in speed, speeding up, it was accelerating. If it was decreasing in speed, it might have an acceleration pointing in the opposite direction of its motion. With projectiles, we had acceleration of the projectile, but only in the y direction, the vertical direction. It could be speeding up if it was falling. It could be slowing down if it was rising, but that was only in one direction. Now we're going to move on from those situations and consider a situation where the acceleration can occur because of a change of direction of the vector. But so far we have acceleration when speeding up, and that would be happening if the magnitude of the velocity, which we just write as v, the speed, is increasing. We can have acceleration occurring if something is slowing down. And that would be if the magnitude of the velocity, which is the speed, is decreasing. Now we're going to consider the possibility of changing direction for another way that acceleration can occur and see how that can happen. Now I want to consider a little bit of vector arithmetic. I'm going to let the change in velocity equal the final velocity minus the initial velocity. That kind of makes sense. We usually define things, if it's a delta, it's the final minus the initial. Now, if I add v initial to both sides, v initial plus delta v, when I add it on the right side, v final minus v initial plus v initial, those two add to 0. This is just going to be v final. Okay, now that's just kind of basic arithmetic, but I can draw this if I have an initial velocity that's in this direction, and maybe I've got a delta v that's in some direction like this. Delta v, remember the way we drew vector addition? We started at the beginning of the first one, went to its end, its head end, and that's where we started drawing the second vector. And when we draw from the beginning of the first to the end of the second, that's how we get the final. Okay, v initial plus delta v is equal to v final. Look at that. These two vectors, v final and v initial, have their tails together. We haven't done that before. I mentioned that when you add two vectors with their tails together, you get the difference between the two vectors. This is v initial, this is v final, and v final minus v initial is delta v. So when I draw it this way, this is actually this vector minus that vector. If I drew it the opposite direction, it'd be this vector minus that one, but we're interested in the v final minus v initial. So keep that little idea in mind because we're going to be using that. A little bit of review about the radian measure of angles. Okay, and I'm going to draw a sector of a circle here and just remind you how radians are measured. This is the radius, still the radius because this is a part of a circle, and this represents an arc length here. Okay. The measure of this angle theta in radians is equal to S over R. And so that's going to be something fairly important in what we're doing. Also, the arc length S is going to equal R theta. Now, in some of what we're going to be doing, we're going to be calling this a change in angle. When something is moving along a circular path, at one time it'll make an angle in some direction, and when it moves to a new spot, it'll make a different angle, and so we'll call that a delta theta, but it's still just an angle. And so keep that in mind. But this all depends on radian measure. We do things every once in a while that are going to depend on radian measure, and a lot of times we'll be looking at very small angles and seeing what the approximations are that we can use in those cases. So on to a new topic here. We've reviewed a couple of things. We want to consider uniform circular motion. Now, we'll before long be getting to circular motion that is not uniform, where something may be changing. It'll still be traveling in a circle, but for now, uniform circular motion means constant speed. Okay, and so the object in the circular motion is going to be going at constant speed. However, if it's traveling in a circle, it's constantly changing direction. That's what we're going to be interested in. I'll start by drawing another sector of a circle, but this is going to be a somewhat larger circle here. I'm going to draw it bigger so we can see some things on here. There's a sector of a circle, and we'll imagine that the object that's traveling along this circular path is going in this direction. Okay, so it's going counterclockwise if you look down on this circle here. And we're going to consider two different times. One when the object is right here, and then when the object is right here. And in both cases, this is the same radius because it's traveling in a circle, always the same distance from this center point here. And we're going to call this angle here delta theta. Okay, if it just sat there, there'd be no change in the angle theta we looked at to see it, but if it's moving, it will be. I also want to draw the instantaneous velocity vectors. When an object is traveling along a curved path, its instantaneous velocity is always tangential to that path. So here's the instantaneous velocity when it's here. We'll call that v initial, and draw another tangent to the path there. Here's v final. Now there's going to be some arc length here, right? And we can write that a couple of different ways, but first I want to make a note of the fact that this is moving at constant speed. So v initial, that's the speed initially, is going to equal v final. That's just going to equal v, whatever the constant speed happens to be. Now, I can express this arc length two different ways here. Okay, that arc length S will equal r delta theta, okay, or S divided by r will equal delta theta, but the arc length is equal to r delta theta. But it's also going to equal v delta t, because it's moving at constant speed. If I just multiply that constant speed by a time interval, I get the distance it has traveled along this circular path. And so I can say that r delta theta is equal to v delta t. Just a lot of abstract stuff so far, but we're doing okay. And let's solve this for delta theta. We're going to find that handy here in a little bit. So delta theta, one weird way to write it is v delta t divided by r. Now, a property of what we've drawn here, This is a radius. V initial is a tangent to that radius. It's tangent to the surface of the circle, and so it's perpendicular to that thing. Okay. V final is perpendicular to this radius. Well, if there is an angle of theta between this radius and this angle, or at an angle delta theta, there will be that same angle delta theta between V initial and V final. I'm going to draw those things on a page by themselves, so let's move on to that. Here we have the two vectors. This is V initial, this will be V final, and I'm going to put arrows on the end of them because they're vectors. This is going to be the same angle delta theta that was between the two radius vectors pointing to those points on the circle. But now I'm looking at velocities. Now, there's an arc length up here, and the arc length will equal the radius of this circle times delta theta. But in this case, the radius of the circle is just v, the speed. So here I can say the radius of this circle, or the arc length of this circle, is going to be r, whoops, not r, but v delta theta. And so it will equal the magnitude of the speed, or just the speed, times that delta theta will be that arc length. But there's another thing on here, and that is that if I draw a straight line between these two things, this is a chord, I think is what you call it, and this is equal to, it's a vector, it's equal to delta V. Okay, V initial plus delta V equals V final. So that's equal to that. Now I'd like to consider two things that are going to happen as the time interval shrinks. Okay. If the time interval shrinks, delta theta is going to shrink. And so this little angle here is going to get smaller and smaller. And I'd like to draw something that's going to occur as that happens. And I'm going to change our scale here. What I've done now is draw a much smaller angle, a shorter time interval. I've drawn my V initial and my V final vectors still pointing out there. They still have the angle delta theta between them. And the two changes that we want to see, one is that the difference between delta V and the arc length, actually I didn't draw a very good arc length. This would be for a circle that the center is at this, it would be much less curved than this. And so it would barely be discernible from this straight line between the two. And in the limit, as delta theta goes towards 0, the difference between arc length and chord length vanishes. If we consider the difference between the arc length and the chord length, as delta theta goes to 0, those two things vanish. And so I can use delta V to represent the arc length if I want to. So I can say V delta theta might equal delta V, or vice versa. This is the first difference that happens. Let's do something with this idea that V delta theta is equal to delta V. And so from before, we're going to use that term for delta theta that we had. Okay, so we've got delta V is equal to V delta theta. And from before, way back when we were considering the simple triangle, or the other triangle, we had that delta theta was equal to V delta T over R. Okay. So I know this is just throwing a lot of math at you, but we're going to end up with something that's Not too bad. So if I take delta theta, which is this thing, and multiply by v, I get v squared delta t over r. And if I divide both sides of this thing by delta t, I end up with delta v over delta t is equal to v squared over r. This is the rate of change of the velocity, and it's purely due to directional change. Okay, v squared over r. Well, that's pretty neat. That's a kind of acceleration that we get just because the direction of the velocity is changing as this thing travels in a circle. We haven't dealt with something like that before. This is sometimes called radial acceleration, sometimes called centripetal acceleration. I tend to call it centripetal acceleration, but sometimes I call it radial. Anyway, get used to that idea. The other thing that changes on here is as this angle shrinks down, delta v, this shrinks closer and closer together, and delta v goes toward being perpendicular to both of these vectors. Okay, you've got an almost 0-degree angle here. These two angles are equal. The angles in a triangle add up to 180 degrees. So as delta theta goes to 0, these two have to go toward 90 degrees. And that delta v will be perpendicular to the instantaneous velocity at any time. So here's what happens. If you have the instantaneous velocity pointing in that direction, it's always tangential to the circle as you're traveling around. The acceleration points toward the center of the circle. When it's back over here, the acceleration is still going to point toward the center of the circle, but in a different direction when it's over here. It'll still have the same magnitude if it's traveling at constant speed. This could be, oops, v final over here. But that's the direction of the acceleration. And it's given by v squared over r. Centripetal acceleration, a new kind of acceleration for that, and that's what we're going to have in circular motion.